In a previous lesson, we looked at the two-source superposition pattern with visible light using a laser. And we said we got a pattern similar to this one here shown on the left, which is the two-source diffraction pattern. And really what we've got here is a series of fringes, light and dark areas on the screen here. This central bright fringe here that we have right in the middle, light arriving from each slit, has travelled the same distance, it arrives in phase, and we get constructive interference happening there in that first maximum there. What we find either side of that is we have a subsidiary maximum here, where at this position light has travelled one wavelength further in reaching that from one slit than the other. And if we go to the other side here, again, light has travelled one wavelength further from one of the slits than the other slit in order to get to that position, and because it's travelled one whole wavelength further, that puts it in phase again with light from the other slit, and we get these regions of constructive interference. At these fringes here, the path difference between the two slits would be 2 wavelengths, and here it would be 3 wavelengths, and so on. And so we get these light and dark areas. Now, the only difficulty with that pattern is that the fringes are very close together because the wavelength of light is so small. Even with the screen here a couple of meters back from the double slit, the fringes will still be close together. Also, because even to get any kind of diffraction, these slits have to be really narrow, the amount of light that's let through is quite small, and so certainly away from the center these will be quite faint, some of these fringes. We can improve the situation if we use instead a diffraction grating. So with a diffraction grating we reduce the width of the slits. Now, reducing the width of the slits will increase the angle through which light is diffracted, and that will produce a pattern where the fringes are further apart, making them easier to see. Of course, if we just had a double slit and we reduced the width of those slits, we would allow less light through, and that would mean the pattern would be much fainter. But with a diffraction grating, you don't just have 2 slits, you have many thousands of slits, and so in total the amount of light coming through is greater. So by having a larger number of much narrower slits, we both increase the intensity of the maxima, but also we increase the spacing of the fringes. Now we can see that here, the 2 patterns on the right. I can't remember exactly how many lines were on these slits. We normally talk, they're so narrow, the slits, we generally talk about them as lines when we refer to a diffraction grating. Typically a diffraction grating would have hundreds of lines per millimetre in each millimetre of that diffraction grating. So in college we have diffraction gratings that are 80 lines per millimetre, 300 lines per millimetre, 600 lines per millimetre. We even got some that are 2,000 lines per millimetre. So here are 2 patterns that have been produced with a diffraction grating here. This one would have been a relatively small number of lines per millimetre. It might have been 80 lines per millimetre. This one here would have been more lines per millimetre. This might have been 300 lines per millimetre or 600 lines per millimetre. You can see the effect here. It produces the fringes. The fringes here are moved further apart. What we've still got here is a central bright fringe where the path difference is 0 wavelengths. Then on either side here we've got a path difference, a fringe where the path difference is going to be 1 wavelength. In other words, here light travelling to this fringe from neighbouring slits has had to travel 1 wavelength further from one slit than its neighbour, and we'll talk about that more in a minute. So we might call this here that might be the 0 order spectrum, would be the 1st order spectrum. We'd have then 2nd order spectrums on either sides, 3rd order spectrums here, where we've got a path difference of 3 wavelengths. Similarly here, central 0 order maximum, then we've got the 1st order maximum, and you can see here how these fringes are more widely spaced. Okay, the order of the spectrum is moved further across here as we increase the spaces between the fringes simply by making the slits narrower. So the more lines per millimetre we have on our diffraction grating, the further apart we will find these fringes. So the principle is the same with the diffraction grating, just as it was with the young slit experiment, the double slit experiment. What we're getting is interference happening. We're getting regions of constructive and destructive interference, these dark areas here. We're getting destructive interference. And at the maxima, the bright fringes, we're getting constructive interference. At the bright fringes, where constructive interference is taking place, light from each slit is arriving in phase. Constructive interference is taking place to produce a maximum. In the dark areas, light from each slit is arriving in antiphase. Destructive interference, cancellation is taking place, and we're producing the minima. So here we will look at the diffraction grating in a little bit more detail. Now we're showing here 3 lines on the diffraction grating, or slits on the diffraction grating. In practice we would have thousands of these lines, it's literally hundreds every millimetre on a diffraction grating, but obviously here for simplicity we're just going to show 3 of those. Now what we've got here is light falling normally on this diffraction grating, in other words at 90 degrees here. You can see a 90-degree angle here between the rays of light and the diffraction grating. Light which then just travels onwards straight through these lines, these slits, will actually then reach a central maximum where we will get constructive interference and obviously a maximum produced. What we can imagine here is light being diffracted towards a subsidiary maximum, let's say the first subsidiary maximum. Now remember, for a diffraction grating, for the pattern that we produce, the distance between the grating here and the screen will be several meters, and the distance between these slits is a tiny fraction of a millimeter. And therefore, if that is the case, these lines that are headed towards that first subsidiary maximum will be almost parallel. We can assume that they will be parallel. We can imagine them being parallel. Okay, obviously they're converging slightly because they're all going to hit that first subsidiary maximum, but the distance here from the diffraction grating to the screen is so much bigger than this distance here between these lines on the diffraction grating that they can be considered almost parallel here. They're virtually, we're going to assume that they're parallel. Now, if that is the case, then if we're producing a subsidiary maximum with these rays of light, the distance here, if you like, the path difference, the extra distance that light travels from this slit compared to the one next to it, will have to equal 1 wavelength. And so we can derive a simple formula here. If this distance here, this extra distance that light from this slit here travels compared to this one, is going to have to be 1 wavelength there. That side is going to be 1 wavelength. We know from trigonometry that this angle here, or sine of that angle, is going to be the opposite side of this triangle here divided by the hypotenuse of the triangle here, which is the spacing between the lines on the diffraction grating. So I can say here that sine theta is going to equal lambda over d, where lambda is the wavelength of light. And so what I have for that first subsidiary maxima, I have wavelength equals d sine theta. Now that's going to be for what we call the first order spectrum. The first order spectrum produced in our diffraction grating is basically the first subsidiary maximum. At the first subsidiary maximum, light from neighbouring slits here, light from one of the slits has got to have travelled 1 whole wavelength further in order to arrive at that maximum in phase with light from the neighbouring slit here. Light from this slit here would have travelled 1 wavelength further than light from this slit, and so they're going to arrive in phase again at that point. Theta here is the angle through which the light makes here from this from the central maximum. So basically theta is the angle through which light has been diffracted to reach that first subsidiary maximum. If light goes straight through, the angle is 0, we get the central maximum, but if it's diffracted through this angle theta here, then we will get here to our first subsidiary maximum. And obviously by geometry, if that angle is theta there, this angle here is going to be 90 minus theta, which means this angle here must be theta as well. So theta, the angle through which light has been diffracted. So let's just think, okay, what about the second subsidiary maximum? When will we form that? Well, we said we've got the first subsidiary maximum here when this path difference between adjacent slits was 1 wavelength. Well, the second one is going to be when that path difference becomes 2 wavelengths. So here, okay, let's say this was for the what we call the first order spectrum. What we can also get is a second order spectrum, where this time light from each slit is diffracted through an angle theta to produce a path difference between light travelling there from adjacent slits of 2 wavelengths. Now again, sine theta then, so theta here, the angle through which the light has been diffracted. If that's theta, this angle here will have to be theta by geometry, as we discussed earlier. So again, sine theta, this time the path difference there, light from adjacent slits, is 2 wavelengths. Of course, the line spacing is still d. So for the second order spectrum, we have 2 lambda equals d sine theta, where lambda is the wavelength of the waves. What we can then do is write a general equation, because clearly we can do this for any order of spectrum. The third order spectrum, okay, if you like, the third subsidiary maxima will be when the path difference between light from adjacent slits is 3 wavelengths. So when the light has been diffracted through such an angle here that the path difference would be 3 wavelengths between the light arriving from adjacent slits. So in that case, we would have 3 lambda equals d sine theta. For the fourth subsidiary maximum, it would be 4 lambda equals d sine theta, and so on. So what we could write here, the general equation would be n lambda equals d sine theta, where d is the line spacing, n is the order of the spectrum, so that would be 1 for the first order spectrum, 2 for the second order spectrum, 3 for the third order spectrum, and so on. And theta is the angle at which that order of spectrum is observed. So it's the angle through which light has been diffracted to reach that order of spectrum. Well, okay, so for diffraction gratings, then we have a formula, n lambda equals d sine theta. So it says the emission spectrum of sodium contains a bright orange line with wavelength of 590 nanometers. Find the angle at which this line would be observed in the second order spectrum when using a diffraction grating of 600 lines per millimeter. Well, how are we going to do that? Well, we're going to use the formula here, n lambda equals d sine theta. We've been asked about the second order spectrum. So n in this formula is going to be 2. And we know the wavelength of this line is 590 nanometers. Well, 590 then, nano means times 10 to the power minus 9. And that will have to equal d sine theta. Now, d is the spacing of the lines in our diffraction grating. What we know here is that we've got 600 lines just within 1 millimeter of this diffraction grating. So generally, when using this formula, what you will have to do is work out d, the line spacing, if you like, the slit spacing, in your diffraction grating, having been given the number of lines per millimeter. So 1 millimeter is 1 times 10 to the minus 3 meters. Within that distance, we've got 600 lines. So if we take 1 millimeter, 1 times 10 to the minus 3 meters, and divide it by 600, that's the number of lines that are in that distance, what we should then get is the spacing just between a pair of lines. So that's worth remembering. To get d, it's going to be 1 times 10 to the minus 3 divided by however many lines you've got per millimeter of your diffraction grating. And then we've got, of course, sine theta, where we are going to want to work out this angle here, theta. So we're going to need to rearrange this equation then. So sine theta. And then once we've got theta, sine theta, we can work out theta. Obviously, if you're hoping to give an answer in degrees, make sure your calculator is in degree mode, not radian mode. And in this case, I've got 45 degrees. So what we would see here, if we used a diffraction grating, we'll have a look at some gas discharge tubes in a minute through a diffraction grating, but what we would see basically, we'd get the bright central maximum, which would contain all of the colours that are in the emission spectrum of sodium sort of on top of each other. But then either side of that, we would get a first order spectrum where we get any lines that we've got in the emission spectrum of sodium, and then further out from that we'd get a second order spectrum where those colours repeat again. And I don't know, we might get a third order spectrum depending on, obviously you can't diffract the light through more than 90 degrees, so with the diffraction grating, as the orders move further apart, you put more lines per millimeter on your grating, you'll get fewer orders of spectrum that are going to be visible, because you can't diffract light through more than 90 degrees. Okay, there we go then. Okay, well here we have again a diffraction pattern here produced using a diffraction grating, but this time what we've used is chromatic light. Now remember, chromatic light contains all of the colours of the spectrum. Laser light is usually monochromatic, will just contain one particular wavelength, but chromatic light here, white light, contains all of the different colours of the spectrum. Now if we view that through a diffraction grating, then what we will get is a pattern that looks rather like this. Now the reason for this pattern is that different wavelengths of light are diffracted by different amounts. Now if we think about our formula that we've just had, n lambda equals d sine theta, so we can rearrange that, and sine theta equals n lambda over d. So here, obviously in the center of this pattern we've got white light. Okay, all the colors are overlapping, but then if you notice here in what we could call the first order spectrum here, the colors are beginning to separate out. Now if we look at this formula, sine theta equals n lambda over d. For a particular diffraction grating, d will be constant, the number of lines per millimeter on that grating. If we look at this, let's say the first order spectrum, red light with its longer wavelength here is going to have a larger angle, a value of sine theta, and therefore a larger value for theta. In other words, light is going to have to be diffracted through a larger angle here to produce a first order spectrum for red light with its greater wavelength than it will be for blue light with a smaller wavelength. So we can see that here on our pattern. If we mark in there the positions of the first order spectrum on either side of this central maximum, you'll notice here on the side closest to the center, what we've got there is a blue fringe, blue tinge to the fringe there, so we're getting the blue light. And as we go to the outside edge of that first order maximum, here we've got red light. If we move across to the second order maxima, so there we've got the second order maxima, and again you can see the colours are separating out even more really there in the second order one. Again, red light, longer wavelength. In the second order n will be 2, longer wavelength, must be a bigger value for sine theta and therefore theta than blue light with that smaller wavelength. So again, inside of the fringe is violet and then blue and red here. And if we go to the third order maximum, you can see here really the blue part of the third order spectrum is almost overlapping with the red part of the second order spectrum here at that point, because the blue light obviously in the third order spectrum is diffracted through a much smaller angle than red light in the third order spectrum, and it's almost the same angle as for red light in the second order spectrum. We've also of course got the third order here on either side. So that's for white light. White light obviously is produced from the light you get from the sun, also from filament lamps, hot metal filaments. As you heat them up, you actually produce a continuous spectrum of light if you get them hot enough. So really, really hot objects, hot solids will radiate light. They'll radiate a continuous spectrum. What we're going to look at just next briefly is a gas discharge tube. Now in a gas discharge tube, what you have is a gas of a particular element that's at very, very low pressure. And we can excite that gas using a stream of electrons. Now remember, atoms basically have electrons in energy levels. These here could represent the energy levels of an atom. If I collide an electron with an atom, the colliding electron may lose some kinetic energy to promote an electron here in the atom from what we would call the ground state, lowest energy level configuration, up to a higher energy level. Now at some point then that electron will de-excite, and as it de-excites it could drop down to one of these other levels. Could, for example, drop down a level at a time. Here, other transitions are possible. It could drop down to that level and then drop down to the bottom. It could just drop straight down in one go. So there's various transitions there that are possible. As it de-excites, as it drops down, that electron drops down to a lower level, it will lose energy. Basically here, this is the lowest energy electron level. This is a higher energy level. So as an electron here, for example, drops down from this level to this one, it's going to lose energy. And that energy then is emitted as a photon of light. HF is the energy of a photon of light. And you can see here there are just particular photon energies that are possible. There's also another transition that will be possible there. It could, once it's got to that level, it could drop straight down as well from there to there. So we've got, you know, 1, 2, 3, 4, 5, 6 maybe different energies that are possible, which will correspond really to 6 lines in the spectrum. So if, for example, we produced a spectrum of light from this atom, once we'd excited it to this level here, we might expect to see not a continuous spectrum as I can see here in the first order spectrum for white light, but we would just see perhaps 2, 3, 4, 6 different lines of different colours here, each corresponding to a particular photon energy. So let's see if we can have a look at that. So here we have a gas discharge tube, which is helium. We'll place that here in the high voltage supply. Put an electric discharge through the tube in order to excite the atoms. You can see it's glowing a sort of a reddy orange colour. And what we're going to do is we're going to use a diffraction grating here of about 300 lines per millimetre. And I'm going to place the diffraction grating in front of the camera and try and show you here the order or the orders of spectrum that we can see. So you can see here clearly, obviously you've got the central maximum right in the middle, and then either side of that you've got a first order spectrum, and then just a little bit further out then you can also see the second order spectrum as well. So you can see there in the first order spectrum you've got a couple of quite faint red lines, you've got a very intense orange line, certainly a green line, a couple of fainter green lines, and then there's a blue line. And then if you could go then further out, you can see that repeated in the second order spectrum, where those lines then are even further apart. Okay, obviously the second order spectrum not quite as bright as the first order spectrum. So this time we have mercury. You can see here the pale blue colour, mercury. But then when we put the diffraction grating in front, you can clearly see the emission spectrum. So you can look there in the first order spectrum, what you've got. You can see clearly a sort of a purple line, a green line, and a fainter orange line in the first order spectrum. And if you look further out, you can just see the second order spectrum where those colours repeat. Again, the purple colour nearest the centre, the green and the orange colour then further out, the longer wavelengths having been diffracted through a larger angle to reach that order of spectrum.